Hi, this is Basma Al-Qadi. I'm presenting an overview of my dissertation work, which is under the supervision of Prof. Malatik, and the work introduces new features based on program slicing for defect prediction. Quality assurance teams in companies are usually limited by time and money, so these companies want to spend their limited resources efficiently on the modules that are most likely to fail, and here where bug prediction techniques usually come. Existing metrics can mainly be categorized into two groups, code metrics and process metrics. Code metrics are directly collected from existing source code, while process metrics are collected from historical data archived in different software repositories. One issue with existing approaches is lacking metrics to estimate program understandability effort. It's been shown that defects are often the result of incorrect understanding of a program segment, so the location of a code that presents a comprehension challenge can be the basis for isolating code that has a greater risk of defects. While software systems have a well-defined syntax, at the same time have semantics, which is hidden deeply in source code, and here we believe that such semantic information should also be useful for characterizing defects to improve defect prediction. Most of the traditional metrics suffer from being very coarse-grained. This nature prevents machine learning algorithms from effectively differentiate between defective and non-defective modules. In practice, employing defect prediction techniques should not be expensive in terms of time. However, widely used process metrics are among the most expensive metrics to collect. So to bridge the gap between program understandability and features used for defect prediction, this work proposes a novel set of cognitive complexity metrics by utilizing program slicing to predict defects. Program slicing provides a semantic view of source code and not only focus on single elements, but it takes the interactions between elements into account. So it can capture more fine-grained features and has the ability to distinguish one code region from another of different semantics. In addition, they are based on static analysis. They do not require the execution of code. They can be easy and automatically collected. The prediction process starts with collecting instances and historic information from software archives. Processing the raw data falls into twofold. First, labeling instances as defective and non-defective, and the second is extracting the metrics using the source slice tool to compute slicing metrics. After generating the corpus, pre-processing techniques are applied, and then we train the model for prediction. Finally, we evaluate the model prediction power. Here is synopsis of the results. The cells in this figure distinguish between the correlation value and correlation intensity that's shown by the color range. Most of the investigated metrics are significantly correlated with defects, and that represent 94% of the cases. And to investigate the prediction power, we compare the proposed model with the baseline metrics model. Overall, slice metrics significantly improve AUC and R-square measures across all systems. Beside the quantitative analysis already performed, we believe it is essential to assess the usefulness of cognitive complexity metrics with the human experiments and evaluate how it can impact in practice. Recently, there is an interest in cross-project prediction. However, most experiments report poor performance since slice-based metrics are of a finer granularity and can capture more detailed view of the modules, so we would like to investigate from this perspective. Using churn of slice-based metrics can also have some potential to predict defects. These measure code churn as deltas of slice-based metrics instead of line-based code churn. Long-term goals are through the combination of slicing with cognitive complexity metrics to enhance resource scheduling, inspection, and reliability. Thanks for listening.